Hey everybody, welcome back. Today I just wanted to talk a little bit about one of my favorite devices in industrial electronics, something that I've been able to work with a lot over the last few years. It's kind of a complicated subject, and so a lot of people ask me about it, mostly just asking, what is it? Why does it work the way it does? What's the big deal? And this concept, this part is called a Programmable Logic Controller, often abbreviated PLC. They're pretty much found in every type of industrial facility that runs anything like a distribution center, a lumber mill, processing, manufacturing. Pretty much everything that has some sort of automation or something that happens automatically runs on some form of a programmable logic control. Even most modern heat, ventilation, HVAC systems in pretty much any facility. So it's found everywhere. That must mean that it's pretty important. There must be some sort of big deal behind why it's so important. And also another big question is, why are they so expensive? If they're so common and the computer technology these days seems like it's so cheap, why are they so expensive? Well, first, let's go ahead and take a look at what is this device. Programmable Logic Controller. Well, it's called logic because when you have input devices, things that tell you something about your environment, like a push button tells you that somebody pressed something, maybe a sensor on a conveyor belt that tells you something's moving past something. All that's input information coming into a system. We then need to be able to make decisions on that. So if the sensor over here is tripped and the sensor over here is tripped, we know that the object must be this long. If it's this long, we then need to make a decision about it. It's making a logical decision based on environmental information coming in. So it's a logic controller. Programmable means that much like building a circuit, you have a very specific purpose. Something that a distribution center that processes packages versus a lumber mill. They might have the same device, but it performs two entirely different tasks. So we must be able to program it. Now, as far as physically what they look like, here's a couple of examples. Although this is just a couple of manufacturers, there's tons of different ways that they look, even from within the same manufacturers. So this first one is a PLC from a company called Siemens. You might recognize that name. They make a lot of industrial automation equipment, a lot of medical equipment, a lot of controllers for building automation. Huge company. They're in all kinds of stuff. But it's a pretty common form factor. That means it's like a shape and size, pretty common for PLCs. There's usually different levels of PLCs. You've got some that are really small like this, and then you've got some that are a whole lot bigger, but they'll have different slots that you can plug stuff into. Don't have a one to show here, but they'll have different slots that you can plug different things into. They call them modular. This one, not so modular. But along the top here, let's open the door and actually take it off. A whole bunch of little screw terminals, and you see a little board installed into this one. It's a cool little device that they plug into here, and it has a whole bunch of little switches. These switches are effectively simulating a push button, a limit switch, a sensor from a device down the line. Instead of the board, you might have actual push buttons and switches in there. Now, they're all numbered along the top, and that helps us locate within the software which terminal number a particular switch is connected to. It's an address, basically, and that's how they're referred to within the software as well, is an address, and that corresponds to a very specific screw terminal out here. Now this one here says 24V DC inputs. Most devices that are push buttons and sensors are small DC voltages. They're a little bit safer. They don't consume very much power. We can also have on here a couple of analog inputs, which mean variable stuff like a temperature. Temperature isn't necessarily an on-off signal. It has a variation. So you might be interested in learning exactly what temperature a particular process is running at, or the position of a control knob, like a volume knob. It's not necessarily on and off, has different values. Now down here, we also have, it says outputs down here. Relay outputs. Relays, I talked about that in a previous video. They're a little bit slow to operate when you compare them to transistors. So nice and tough. They have a lot of various voltages that you can run through them, so they're not very restrictive, but they are pretty slow, so we can't usually use them for motor control. Now this one up here says AC, DC relay. AC because the power that we plug in up here is 120 to 240V AC. The second set, DC, says the inputs, they're DC inputs, and then relay is for the relay outputs. So they, on this line of PLCs, they number them and name them according to what their function is. Now down here, this is a really important part of PLCs. This one looks like an Ethernet connector, and that's actually what it is, or very similar to it, Profinet. Profinet is a variation of Ethernet. and that allows a computer to talk to the PLC and program it, but it also allows a PLC to talk to other things. For example, here we have a big touch screen, and this touch screen right here has an Ethernet port. It also has a few other things, some ports to be able to connect to it and send its program to it, but eventually we usually want to be able to network stuff. In today's day and age, it's really common for things to be networked together. So if a PLC is purchased that doesn't have networking capability, your usage of that is going to be pretty limited. It's going to be what they might call standalone, or it's the only one that can exist in a machine. Another really common brand is Allen Bradley, also now Rockwell Automation. They're the owner of the Allen Bradley Controls Department. So this one, you'll notice a lot of similarities to it. The fact that the doors can come off, and it has a bunch of screw terminals on the top and bottom. Now this one up here says DC 24 out. It also says the 85 to 264 VAC. This is the input. Now it is AC powered. Right over here we see AC power. We also see DC input relay outputs. So just like that previous one, on the Siemens one, they labeled exactly what the functions were. This one's same deal. We have DC inputs, just like before, relay outputs, just like before, and AC inputs, or AC power, just like before. Now up here, I, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. You said 9. That means that there's 10 inputs. We start at 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Kind of an unusual way of counting, but for computers, it's really common. Here's our outputs, or O, 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5. So that's six outputs, 0 to 5. Starting at 0, counting again. Now this one has a kind of a unique connector. It's a very industry-specific connector on. It's not a USB cable or an Ethernet cable or something. Most modern processors are going to be connected either a USB or an Ethernet cable. This one actually has become outdated. This is the Micrologix 1000. They've replaced it with other ones. Still a nice little controller to use, but it really does not do well at talking to the outside world. Great for working its own little machine, its own little process, but hard to make it talk to other stuff. Now here's one that actually, you'll notice from the top, looks almost exactly the same, but a little thinner. This one does not have the AC to DC power conversion, so when you power it, down here it says, get that shadow out of the way, DC in 24 volts. So it says DC power, not AC power. So it requires an external power supply. And there. Because of that, this one says not used up here, because you must already have a DC power supply. The other one includes a DC power supply because it's not guaranteed that your system is going to have a power supply just because it's powered with AC. So a lot of different variations of these. But a big question to ask is, why are they so expensive? For example, some of these things, this one and this one, these ones are the very lowest end of PLCs, and they can cost in the hundreds of dollars. We can get a whole refurbished laptop that probably outperforms these in every way, still cheaper. How is that possible? In fact, we can take that a step further, and we can also find all kinds of these little microprocessors. They call them microcontrollers. Okay, these microcontrollers. So this thing right here costs about $20. Sometimes you can find variations that are even less than that. This is the entire processor. It can run sometimes faster than a PLC. There's some variations of this that can run way faster. Inputs and outputs. Remember we said there was 10 inputs and 6 outputs? Okay, that's 16 total. This thing has 14. This one right here has 56 inputs and outputs. Now we have to add a little bit of extra circuitry to protect them from the 24 volts. It's made for 5 volt stuff, but USB cable, so I can program it. This is the entire processor, way faster, more memory storage. Well, actually that may not be entirely correct. Different generations of PLCs have different memory abilities, but a PLC may only have a couple of megabytes of storage space. So we don't think about them like a computer with gigabytes of storage. And then here's one. This one is just as fast, fairly decent amount of storage space. Its limitation is it doesn't have very many inputs and outputs, just those little copper circles around the edge. But this thing is tiny, it costs about $5. So there again, why are these things so expensive? And really one of the main things is the programming software and the reliability of these things. You have to know C++ or Python or Java or other programming languages to program these things, but you have to understand electrical wiring to program these. Very handy in industrial setting. A lot more people are going to understand industrial wiring and understand how to troubleshoot and fix these when they fail, as opposed to something like this, where you basically have to be a computer scientist or an IT professional to troubleshoot and solve one of these. So after getting a little bit of a clearer understanding of what these programmable logic controllers are, what they do, and then some of the lower cost alternatives, if you're still curious about any of these things, or if you have ideas on systems that might be benefiting from using some of these kinds of devices, just let me know. Shoot me an email or a comment or something, and let me know what kind of devices you'd like to see. It's definitely an interesting world to explore. It's really not as expensive as a lot of people think. It's not nearly as complicated as most people think, but it's very tricky to dive right into. So that's why it's helpful to kind of see a purpose, have a plan in mind, and then see how you can achieve that through implementing some of this technology. So if you're curious, definitely let me know. But the best practice is just to go out there and build something. That is the best way to learn how something works. Okay, that's all for now. Go build something.